Hello, my name is Horvat from the University of Ljubljana, Slovenia. And today I would like to talk to you about flattening knotted surfaces. First, I would like to thank the organizers of this online seminar for the invitation and for the opportunity to speak here. So first I'll say something about the introductory motivation for this work and for the background that comes from classical knot theory. Then I will present the flattenings of surfaces and the invariants that come from those. So the original motivation for my work comes from the fibrations of four manifolds. It's well known that the topology of four manifolds may be studied by looking at several fibrations of a four manifold over a two manifold. The most natural example are the Lefschetz fibrations on complex manifolds, which also have generalizations in broken Lefschetz fibrations and Morse to functions, and finally trisections that actually exist for every smooth four manifold. So my goal was to observe and describe embedded surfaces inside a four manifold using two-dimensional projections. The original construction comes from the Morse functions on classical knots. So the setting is the following. If we have a classical knot inside the three-sphere, then we may consider the collection M of k of all Morse functions on the three-sphere with exactly two critical points, such that the restriction to the knot is also a Morse function. For any function h from such a collection, we may look at the critical points of the Morse function and choose one regular value inside each regular interval, and then count the cardinality of the fiber above a regular value. And by looking at these numbers, we may consider three values. These are the numbers b of h, that's the number of maxima of the Morse function, h restricted to k. The trunk of h, this is the maximal cardinality of the fiber above k. And w of h, this is the sum of all cardinalities of the fibers. And then by taking minima of these numbers over all Morse functions from M of k, we obtain three knot invariants: the bridge number, the trunk of a knot, and the width of a knot. And my goal was to take this construction one dimension higher, that is to say, to define similar invariants for embedded surfaces inside the four-sphere. The general setting is described in this proposition. So if we have any four manifold X and a smooth map from X to a two-manifold sigma, which will usually be a two-plane or a two-sphere, then we may consider the set of critical points of the restriction of this map to an embedded surface K. And the cardinality of the fibers of this restriction is constant on each connected component of the complement of the critical value set f of A. So now I will describe the setting which I will need for my construction. First, we recall the hyperbolic splitting of a surface. So a Morse function h on the force sphere is called a hyperbolic splitting of an embedded surface K if it satisfies these conditions. H needs to have exactly two critical points, and the restriction of H to the embedded surface K is also a Morse function. All its minima should occur in the -1 level. All its maxima should occur in the 1 level, and all hyperbolic points of H restricted to K should occur in the 0 level. It's well known that each embedded surface inside the force sphere admits such a hyperbolic splitting. And actually, such a splitting also admits a natural diagram of an embedded surface that is called a marked graph diagram. So if we take a hyperbolic splitting of surface K, then the 0 section, which we denote by K0, is an embedded four-valent graph whose vertices correspond to saddles. So they are the critical points of index 1. And by choosing a regular projection P of the 0 section to sphere sigma, we obtain a diagram gamma, which is again a four-valent graph embedded in the two sphere. And this diagram, this graph, has two kinds of vertices. Some vertices are correspond to the crossings of the diagram. So they are endowed with the information about the overcrossings and undercrossings, while some of the vertices correspond to the saddles, and these are endowed with markers. In this figure, a marker is denoted by a green rectangle. And such markers also determine the resolutions above and below this 0 section. Such diagrams were first introduced by Yoshikawa. Now I will say what flattening of an ordered surface is. So we start by an embedded surface in the force sphere with a hyperbolic splitting H. And we denote by C of H the two critical points of this hyperbolic splitting. Now we know that H defines a marked graph diagram, gamma, that I described just now. And then H actually induces a map I will define that will be denoted by H perpendicular from the force sphere without the two critical points to a two-sphere sigma. And it will turn out that the set of the critical values of this map is actually equivalent to the marked graph diagram gamma. So how do we get there? Denote by phi the flow of the gradient vector field of H, and choose a regular projection P of the zero section to a two-sphere sigma. Then the map is defined by first pushing everything towards the zero section by this gradient vector flow. And then when we get to the zero section, we project by this regular projection P. So we obtain this map from the fourth sphere to the sigma that is not defined at the two critical points. And it turns out that this map is smooth and its restriction to the embedded surface K will be called a flattening map. If we think of the hyperbolic splitting as a height function or on our embedded surface, then this flattening map can be thought of as a map that flattens our surface against this two-sphere sigma. And when we flatten an embedded surface, we should obtain creases at along some curves. And it turns out that these creases are actually simple to describe. So this is written in the proposition here. So if we have a hyperbolic splitting that induces a flattening map, as described above, this hyperbolic splitting also defines a marked graph diagram gamma, and the set of critical values of this flattening map is actually equal to gamma. So we have a nice description of the critical value set. This is the set of the creases, as we may imagine. To see this, you may observe that when projecting with this flattening map, the zero section of the surface, K0, is exactly the set of points at which the gradient vector field is tangent to the surface. And so at those points, the rank of the map won't be the maximal rank. And using our projection P, this zero section goes exactly to the marked graph diagram gamma. Okay, so from this setting, when we have a flattening map defined by a hyperbolic splitting, and the diagram gamma that is a nice picture of this critical value set, then we call the components of the complement of gamma in the two-plane sigma regions. And these are actually the analogs of the regular intervals we had at the beginning when we considered Morse functions on classical knots. And the multiplicity of the flattening map in a region U is defined as the cardinality of the fibers above U. So this is denoted by M here. Once we have these multiplicities, we may endow our diagram with them. And this is seen here in the case of the spin of the trefoil knot. So it's easy to see that since we have closed embedded surfaces, the multiplicities will always be even numbers. Now, in order to construct invariants from flattenings, we denote by h of k the family of all hyperbolic splittings of an embedded surface k. And each hyperbolic splitting from this family defines a flattening map from K to a two-sphere sigma. And the set of critical points of this map is the marked graph diagram gamma. Now it turns out that the separation of the two-sphere by gamma is not quite generic. This is why we need to introduce the notion of inessential vertices here. So a vertex of the diagram gamma is called inessential if it is a marked vertex that represents a branch point of the flattening map. And two regions of the diagram are then called equivalent if they are incident to the same inessential vertex and actually become identified when we pass from the zero section to its resolution above the zero section. So this defines an equivalence relation on the set of regions of the marked graph diagram. And in this figure here, you can see two colored regions that become identified, so that are equivalent. And two equivalent regions, in two equivalent regions, the flattening map always has the same multiplicity. So, okay. Now we just take our marked graph diagram and denote by U0 to UN its regions. And then the equivalence relation on the set of regions induces an equivalence relation on the index set from 0 to n. And we denote by I the quotient set by this equivalence relation. So we count everything modulo this equivalence. Now we may define three numbers. P of h denotes the number of regions, equivalence classes of regions where the flattening map has positive multiplicity. Trunk of h denotes the maximal multiplicity of the flattening map inside the region, and W of h denotes the sum of all equivalence class multiplicities over all equivalence classes of regions. Then we just take the minima over all hyperbolic splittings from h of k and obtain three invariants that come from a flattenings. So P of k is called the partition number, trunk of k is called the trunk, and the W of k is called the width of an embedded surface k. Now it's easy to see that these three invariants are related to some extent. This proposition describes this relationship. Okay, and now we have the setting where we may consider the values of these invariants. So first we consider the unknotted orientable surfaces. Recall that an orientable surface in the force sphere is called unknotted if it is a boundary of a handle body. And this is a simple marked graph diagram of an unknotted orientable surface of genus G, where the number of circles in this diagram should be G plus 1. So this lemma says that the number of the invariants for the unknotted surfaces is what we should expect, so the smallest possible positive number. This is the fact because the regions in this diagram in which the flattening map has non-zero multiplicity are actually all equivalent. So we just have P of k equal to 1, and the trunk and the width are both equal to 2. Okay. Then the obvious question is how the invariants behave under connected sum of surfaces. So if we have two embedded surfaces, K1 and K2, then each of them may be represented by a marked graph diagram that corresponds to a hyperbolic splitting. And we may do a connected sum of these two diagrams by identifying two regions of these diagrams. And these regions are actually the regions with lowest positive multiplicity. So it's not hard to see that the values of the invariants for the connected sum will satisfy these inequalities. So the partition number should be less than or equal to the sum of both partition numbers minus 1. The width should be less than or equal to the sum of the widths minus 2, and the trunk will be less than or equal to the maximum of both trunks. Okay. Then we look at span knots. These are the simplest examples of two knots in the force sphere. A span knot is obtained by taking a one knot in the three sphere and then removing an arc from this knot to obtain actually a one tangle in the three ball, and then spinning this one tangle around the boundary to sphere to obtain a knotted annulus, and capping of this knotted annulus by two discs. So the two knot obtained by this construction is denoted by S of k and called the spin of the one knot k. Now we obtain this inequality. So if we have a one knot with bridge number B of k, then the spin of k will have the trunk that is at most 2 times B of K. This is obtained by taking a suitable diagram of K that is given as closure of a braid on 2 B of K strands, and then deriving the diagram of the span of K that is drawn here. And then we just need a simple argument that takes into account that the difference between the region multiplicities of 2 adjacent regions is always equal to 0 or 2. Okay, an interesting family of 2 knots to consider together with our invariants are the satellite 2 knots. First, we recall the construction. So let Kp be a 2-sphere embedded in S2 cross D2, that is called the pattern. And let Kc be a 2-sphere embedded in S4, so a usual 2 knot with a tubular neighborhood nu of Kc. Then we choose a diffeomorphism F that identifies S2 cross D2 with this tubular neighborhood, and this gives us a satellite knot F of Kp. This is a satellite with pattern Kp and companion Kc. Now, to take an example, on the left here, you can see a simple pattern that just winds around the 2-sphere 3 times, so that its winding number is 3. And on the right, you can see the spin of the figure 8 knot and its marked graph diagram endowed with the multiplicities of the flattening map. So if we take a satellite knot with this pattern and companion, we obtain 2 knots with this diagram, which is quite interesting to study because it's obvious that we obtain quite many regions, and some of these regions originate from the regions of the companion knot. Some of them originate from the regions of the pattern, and it's not difficult to relate the multiplicities of these regions with the multiplicities of the 2 knots. So, for example, the regions that come from the companion knot, their multiplicities are just multiplied by the winding number of the pattern. And we also have a lot of rectangular regions in this diagram that come from either the edges or the vertices of the companion knot diagram. So by carefully analyzing all types of the regions, we obtain here, we may say a lot about their multiplicities, and then try to say something about our invariants of satellite knots. For example, we may obtain this result. So if we have a satellite 2 knot with companion Kc and pattern Kp, And if omega denotes the geometric winding of the pattern, then the trunk of the satellite will be bounded above by the maximum of omega times the trunk of the companion knot and the trunk of the pattern. So for the classical knots, we do know that the bridge number and the width of satellite knots are related, and it might be interesting to find some relationships for these invariants in the case of satellite two knots as well. Besides the invariants I presented here, that are in their nature topological, we might also consider geometric invariants that come from the flattenings, such as the shape of the regions or the number of vertices of given type. So if we have a flattening of an embedded surface K, then the closure of each region in the two spheres sigma is actually a curved edge polygon whose vertices are the vertices of the marked graph diagram. And we denote by U hat the union of all regions equivalent to U. Then a suitable number to consider or to investigate is the number of essential vertices in the boundary of this U hat. This would take into account the geometry of the situation. So if, again, we denote by U0 to UN the regions of our diagram, and then take as I the set of all equivalence classes of indices, then we may consider S of H, which is the sum of these numbers, S of UI over all equivalence classes of regions, divided by the partition number of H, and then again take the minimum of all these values over all hyperbolic splittings of the surface. So this defines again an invariant of embedded surfaces, and it turns out that this invariant distinguishes unknotted surfaces. So an orientable closed surface in the fourth sphere is unknotted if and only if its shape invariant equals 0. I think it's quite curious, and this is one of the possible directions for further study of my work. So to investigate this shape invariant and to see what its values are, because it's you see here, this is a rational number, and to see whether we can say something about this invariant for some classes of embedded surfaces, maybe what it says about the properties of an embedded surface, and so on. Other possible ideas for further study is to see what the relationship between our invariants and the bridge number of knotted surfaces is. So Meyer and Spun, in their work about the trisections of embedded surfaces, defined the bridge number and also found some interesting results about this number for several classes of surfaces. And it's an obvious question of how this invariant, the bridge number, relates, for example, to the width or to the trunk of embedded surfaces. Another perspective on this relationship would be to see what, how to relate the flattenings and trisections of embedded surfaces, this two different kinds of diagrams. I would also like to understand this relationship. Then the possible way, as I mentioned earlier, is to study the width of satellite 2 nodes and see whether it has some relationship with the bridge number or the other invariants. And of course, this construction could also be generalized to the surfaces in any closed for manifolds, and it might be interesting to see some new insight obtained by the perspective of flattenings. Okay, and these are just some of the references I used. Thank you very much for your attention. Goodbye.